All right, here we go. Type 1, which is rate and accumulation. Now, even though this says BC number 2, this was a shared problem in 2013. So it's 2013, but it was a shared problem between both AB and BC. All right, so you were given G of T, which is the rate at which unprocessed gravel arrives at a plant. I would encourage you to graph this in your calculator. That would also give you a mode check to make sure that you're in radians and make sure you set your appropriate window. Okay, we also know that there's 500 tons of gravel at time t equals 0, and I want to remind you just to always look for that initial value that might be given in the stem of the problem. We're to find G prime at 5 using the calculator, and then using the correct units, interpret your answer in the context of the problem. So I just use this G prime of 5 from the calculator, directly from the graph, in calc, second trace calc, and then you can find the derivative there. The meaning, there's always going to be 3 parts. At t equals 5, or you can say 5 hours after the plant has opened, the rate at which the unprocessed gravel arrives at the gravel processing plant is decreasing. Okay, what's happening? Okay, at a rate of 24.588. And then here are your units, tons per hour per hour. So here's your little sort of reminder. You're going to need time. So at t equals 5, you're going to need your units. In this case, it's tons per hour per hour. You're going to need to know what is happening. So this is the rate at which the unprocessed gravel arrives is decreasing at a rate of. So it's a rate of a rate. Part B asks for the total amount of unprocessed gravel that arrives in the hours of operation, which are from 0 to 8. So again, we're just integrating, and if you've already graphed this in your calculator, you're just going to find the area underneath the curve G of T, and that's 825.551. Part C is asking whether the amount of unprocessed gravel at the plant is increasing or decreasing at t is equal to 5. So G of 5, the rate at the unprocessed gravel arrives, is 141. The rate at which the gravel is processed is constant at 100 tons per hour. So since 98.141 is less than 100, we know that the amount of unprocessed gravel is decreasing at t is equal to 5. Part D is asking what is the maximum amount of unprocessed gravel at the plant in the hours of operation. So we're looking for when the maximum occurs. And remember, we have rate of unprocessed gravel coming in and then rate of processed gravel. And so I want to know when that equals 0. So this is the difference of those two rates. And I want to know when it's equal to 0 or when they're equal to each other. That happens at time 4 equals 923. I'm going to store that in A because I'm going to need that. All right. We use our candidates test. We know at time t equals 0, we're already 500 tons of unprocessed gravel. At time t equals 4.9323, which I've stored in my calculator without that truncated rounded value, I have 500, and then the area underneath the curve, or the integration from 0 to A, remember I stored that 4.923 in the calculator, of G of T minus 100 dt. That gives us about 135.376. At time t equals 8, which is the other endpoint. Okay, so I'm going to go from 0 to 8, or you can go from 4.923 to 8, and that gives you 500 plus this 135 minus 109. Okay, so the max amount of gravel at the plant is going to happen at time t equals 4.923, and that's 635.376 tons. All right, the second one in this packet, 2015 number 1, again it says BC, but it is a shared A-B problem as well. So we're given the rate at which rainwater flows into a pipe, and that's 20 times sine t squared over 35. We're also given the rate at which water drains out of the pipe, And then at t is equal to 0, we know we have 30 cubic feet of water already in the pipe. So how many feet of rainwater flows into the pipe in those 8 hours? That's going to be 76.570. And again, since this is a calculator problem, I integrated or found the area underneath the curve just from the calculator. Part B asks, is the amount of water in the pipe increasing or decreasing at t equals 3? So we found what the rate of the water flowing in and the rate at which it's draining or leaking. And since R of 3 is less than D of 3, then the amount of water in the pipe is decreasing at t is equal to 3. Part C wants to know when, at what time t, the water is at a minimum in the pipe. So again, we're looking for when the rate is 0, or we want to find the critical number. So it's R of t minus D of t equals 0, or when is R of t equal D of t? That's when it's going to change from something being increasing to decreasing. That happens at 3.271. Again, I store that in my calculator. At time t equals 0, we already know we have 30. At time t equals 3.271, I found the area, it's 30 plus the area underneath the curve from 0 to t1, which is 3.271. That actually gave us a negative 2.035, and so that's going to give us a little under 28 cubic feet in the pipe. At t is equal to 8, that's going to be 30 minus that 2.035, and then that's going to add from that time t equals 3.271 to 8. We're going to add an additional 20.579. So the time at which the water in the pipe is the minimum is 3.271. All right, part D. We know our pipe can hold 50 cubic feet of water before it overflows. And so we want to find the time W where this is going to overflow. And you're to write, but not solve, that equation involving one or more integrals that gives the time W when the pipe overflows. So remember, we start out with 30, and then we're going to go from 0 to some time W. And again, this is the water that flows in right here minus the water that drains, and that can't be any more than 50. Okay, so that we're just going to set it equal to 50, and there's your equation. All right, question 2000, AB number 4. This is a non-calculator problem, or you don't have your calculator. We have rate in of a constant 8 gallons per minute, and rate out, the amount that the water leaks out, is the square root of t plus 1 gallons per minute. And part A asked how much gallons of water actually leak out from the time from 0 to 3. And so you're just going to integrate from 0 to 3 of that t plus 1 to the 1/2 power. Again, we're going to, add that little plus 1 when we integrate by taking the reverse power rule. When I get that, I get 2/3 t plus 1 to the 3/2 from 0 to 3. I plug those in by FTC number 1. Oops, little mistake here. There should be a minus. Okay. You don't need to simplify that expression at all. You can leave it just like that. Or you can leave it like this, really doesn't matter. Or you can say 2/3 times 7 or 14 thirds. All right, part B asks how many gallons of water in the tank at t is equal to 3. So remember, that's going to be that initial value, 30 gallons is in there at t is equal to 0. Then we're going to have the amount that flows out, the total amount, which is the integration from 0 to 3, the square root of t plus 1 dt, plus the amount that flows in. And we have a constant amount of 8 gallons per minute. All right, and I already know this answer from above, negative or 14 thirds, which is when I take that away. So 30 minus 14 thirds plus 24. You don't need to simplify, but if you do, you should get 48 thirds. All right, part C asks you to write an expression for A of t, the total number of gallons of water in the tank at time t equals t. Okay, so we have that 30, and then I'm going to integrate from 0 to t, because it's asking for an equation in terms of t of 8 dx minus the amount that leaks out from 0 to t of the square root of x plus 1 dx. You can combine those into one expression if you'd like. Part D asks at what time between 0 and 120 minutes is the amount of water in the tank a maximum. Again, you don't have a calculator for this problem. So what happens here, we want to know when that derivative of the amount, because we want to find its maximum, so we're going to set its derivative to 0. Okay, so I just end up with a prime of t equals 8 minus the square root of t plus 1 that comes from ftc2 from that expression. We just took the derivative right there. I set it equal to 0, solve for t. Now, we can use the candidates test. The problem with the candidates test is the integration gets a little bit messy in here. So because you only have 15 minutes, or you may have 25, but you only have 15 minutes on a typical AP exam, I'm going to check what happens to A prime, and specifically what happens to A prime at 63. And so at A prime less than 8, or excuse me, less than 63, I picked 8 because when I plugged in 8 into the derivative, it became positive. So I plugged in and up here, and I picked 8 because 8 plus 1 is 9. We can easily take the square root of 9 without the calculator. And then I picked 80 because, again, 80 plus 1 gives us a nice little perfect square, and I get something negative. Okay, so because the first derivative changes from positive to negative, when t is 63, we know that a of t has a max. Now, if you go through the candidates test, we know we have 30 here. We integrate this piece and from 0 to 63 or from 0 to 120. And it happens that the maximum does occur at t is equal to 63. Right. We only have 3 multiple choice problems here. Number 8 asks you to use a right-hand Riemann sum to approximate the number of liters of oil that are in the tank in 15 hours, or at t is equal to 15. Again, we start with this 50, our initial amount, and then we approximate the area underneath the curve with this right Riemann sum right here. Okay? And we get 50 plus 64.9, and again, this is probably without a calculator, but it might be with a calculator. And you get 114.9, or choice C. All right, in 81, this is probably assuming you have a calculator, and again, you're trying to find if the tank contains 800 gallons of water when the pump was turned on, how much water to the nearest gallon after 20 minutes. So again, we're going to integrate that R of t from 0 to 20. We know we start with 800. From 0 to 20 underneath this rate curve, that's 420.143. To the nearest gallon, that's going to be choice D, which is 1,220 gallons. And the last one, 89, we have a particle that moves along the line such that we have this acceleration. We know the velocity at time 0 is 5. We're looking for the velocity at time t equals 3. So using FTC number 1, okay, which is important, we know that the area underneath the curve from 0 to 3 of a of t, but remember, a of t is equal to the derivative of v of t. Okay, that's going to give us v of 3 minus v of 0. Sliding that around, sliding that v of 0 over to the opposite side of the equation. V of 0 we know is 5. Using our calculator to find the area underneath the curve from 0 to 3 underneath this a of t that was given, we get 6.710, and we add that and we get 11.710, or choice E.